All right. Well, thank you very much, everybody, for attending this Thermal Transport Cafe. If you've been attending the past few this semester, we've had some really nice talks on some experimental research, a very microscopic level to kind of more macro scale research on condensation. So today we're really excited to have a more numerical and data-driven based talk that Dr. Romit Maulik is going to discuss. So Dr. Maulik is an assistant professor of data science in the College of Information Science and Technology at Penn State. And he also has a joint appointment at Faculty of Mechanics and Computer Science Division at Argonne National Lab. He got his PhD at Oklahoma State University in 2019 and was a Butler Fellow and a staff scientist at A&L before joining Penn State. So his research, I mean, he'll talk much more about it in much better detail, but it's basically at the intersection of machine learning with high fidelity simulations. So he's led many research projects and is already very heavily awarded and an early career awardee of art from the Army Research Office. So we're really excited to have him showcase his work here, and we're really looking forward to it. So the floor is yours, Romit. Thank you very much.
All right, thanks. Thank you for the invitation. Thank you for having me. I want to start by saying that this talk does not have a lot of thermal in it. It has a little bit of transport, and I have coffee on the side. So I guess 2 out of 3 to start with. But thanks a lot for the invitation. Happy to be here. I'm going to talk today about some work we are doing in uh, scientific machine learning, which is a new paradigm for enhancing scientific computing with the fact that we are collecting various sources of data. There's another keyword over here, differentiable physics, that connects to, say, some of the physics topics that the members of the audience may be interested in, right? So let me also get my laser pointer going, right? So feel free to stop me at any moment. I like questions while I'm speaking. But you can also reach out to me after. Happy to discuss more. Okay, so for people who do numerical simulations, let me see if I can minimize this so that it doesn't interrupt me. So for people who do numerical simulations, which is a lot of us, one of the things that a general framework that we typically follow is the formulation of a system of equations, which usually comes from some knowledge about the physics that we're trying to simulate in the form of conservation laws, the governing laws, and a general setup for something like this, which shows up in a lot of different applications, is a system of nonlinear partial differential equations, so Navier-Stokes, magnetohydrodynamics, heat and mass transfer also, which couples with Navier-Stokes. And you typically have a dynamical system. A lot of my examples today will be dynamical systems, so that's why I leave the unsteady term in there. But this doesn't have to be restricted to dynamical systems. Some initial conditions and boundary conditions. So once you set up a formulation like this, a legacy approach to simulations would use workstations or high performance computing resources to discretize these governing laws and then make forecasts, typically by solving linear systems iteratively, for example. And classical simulation-based research has led to transformative advances in the world around us, right? Think about something like the weather. You get it on your phone, but there's really very large simulations that are running under the hood in data centers distributed geographically that lead to these forecasts. Similarly, if you're doing design or control or optimization, and you have the luxury of large computing resources, then classical simulation-based methods are really a go-to tool for at least a portion of your engineering design phase, right? Of course, experimentalists are required for validations and so on. But there are a few common bottlenecks in simulation-based research. Firstly, there are you're assuming a set of laws which you may not know, or there may be imprecision in both the laws as well as the initial and boundary conditions. And many times in many realistic applications, especially, for example, if you're someone from the fluids domain, you may have to unreasonably simplify your simulation just to complete a run. So and this kind of causes simulation-based research to be limited for real-time applications, right? Something like digital twins, which is kind of an interesting area of research now, where you want to run a simulation in real time. So as your physical process is happening, you also want your numerical simulation to be run at the same time. But if you have to unreasonably simplify your numerical simulation just for a real-time output, then you may not have a high fidelity output, right? So this is some challenge with classical computer science. Now, in recent times, because of sort of the transformative advances in GPU computing and machine learning, one approach to say addressing the problems with classical simulation-based modeling is this idea of a purely data-driven model. I have a schematic here from a paper that was published in about 5 years ago now, but from Google, where I mean, you don't have to worry about the details over here. It's not really relevant to this talk, but the idea is that they were developed a new machine learning model that could essentially convert a simulation problem into a video generation problem, right? So given, the state of the dynamical system at a particular time step, they would have a purely data-driven evolution of the state. And they demonstrated on a few pretty complex problems, such as like a dam break or a multi-phase flow dam break problem, which is quite exciting because it actually addresses some of the problems with simulations, such as not requiring a very fine time step, uh, uh, the capacity to deal with coarser resolutions, and so on. However, there is some problem. There's no free lunch. There's a problem with this approach as well. The data that you have may typically not be available at the desired fidelity, right? So if you think about the data that we do collect about physical processes, you either have you have to either use experimental data, which will of course have its associated errors, and there is also this argument out there that you actually need fully resolved data for your problem to actually then build a data-driven model. Then in some sense you've already solved your problem and trying to solve it again with a different method. So there's this criticism of that approach, right? So typically, you would want to use data that is cheaply available, and that itself may be generated through approximations. And so you're back to square one. You're learning a model that's not very accurate. And then, of course, there are many situations where you just don't have data, right? You may have some approximate knowledge of the physics, but your data is very sparse or not very informative about your physics. And so, again, this approach, while promising, then has an issue of scaling to realistic applications, right? So what scientific machine learning does, or the broader sort of field of scientific machine learning, is that we want to retain, the nice things about classical simulation-based modeling, which is, imposing some set of governing laws and then using either a continuous or discrete representation of the same, but using data when it's available to sort of guide our modeling strategy, right? So I have an example here on the right-hand side, where let's say you try to, this is a damped pendulum measured over time, the position of the damped pendulum. So the yellow points are, data that you've collected by observing the pendulum, and you try to fit a model, just a purely data-driven fit of the model. And as you can see, you get a typical failure mode for all data-driven methods, which is you fit your data really well, but then as you sort of extrapolate or you try to predict out into the future, this model fails. A scientific machine learning approach here, using the work by the group in Brown University, who pioneered a lot of this research, the physics-informed neural network. You can see that by imposing the fact that something about the behavior of a pendulum, right? It's defined by an ODE. You can actually not only fit the data that you collect, but the fact that there are losses that you also try to that you try to preserve. For example, these governing laws, you can actually get better performance out there, right? So this is the scientific machine learning approach. There are some challenges with this approach as well, which is why I will not be using a physics-informed neural network. I'll be using differentiable physics, which for certain cases is superior. The challenges of this approach are, well, I would like to highlight number 2 first, which is while you do get fits, right? You do get a model that is able to predict your data and then extrapolate better. There is an unclosed loop. Modeling should lead to scientific discovery. That was why people build models. And so this is not clear as how it is not yet quite clear how data-driven model actually tells you something that you did not know about the physics. So that's something that is of prime importance. I should probably move this to bullet point 1, but just wanted to highlight that. In many cases, you may not know your governing equations exactly, right? So in this case, we know the governing equations of the pendulum, so you can enforce them. Many applications, your governing equations are approximate, so there are limitations over there. In most of the scientific machine learning literature out there, there is a minimization that is set up usually in the 2 norms in the sense of a mean squared error. And so such an objective is differentiable, and that's why it's convenient to use. But in many applications, such as the ones I will be explaining to you, I'll be sort of introducing to you and explaining to you, you will see that mean squared error is perhaps not the best metric in the sense of the scientific value of your simulation, right? Maybe you're interested more in kind of like a probabilistic metric, which is not easy to collect or is not easy to differentiate. So in such cases, such models can also be challenging to use. And finally, at least the point number 1 is related mainly to a lot of methods where you impose constraints related to your scientific computing equations, your governing laws in a weak sense as a Lagrangian penalty. These can be difficult to optimize for. So just something, if people are familiar with pins, they will know what I'm talking about. Okay. So that brings me to the paradigm that I'm trying to introduce to you today, which is differentiable physics. The idea is to kind of combine the best of several worlds. So firstly, the idea is that if we have built some capability in scientific computing where we know how to efficiently discretize a system of equations, assuming we have a system of equations, we know how to scale these discretized models. We know something about convergence guarantees. We also understand inverse problems. Then we should preserve these while also leveraging advances in machine learning, such as physics-informed methods or operator learning, and we have some examples going forward. In addition, since we know inverse problems, we should also be able to learn from data of various modalities and fidelities. So for example, in a problem, you have data coming from numerical methods, numerical experiments, which are maybe not as accurate because that's all you can do. You might have data coming from experimental observations. How do you leverage data of varying modalities into your machine learning approach, right? So this is kind of like making sure no data is left out and experimentalists are included in the modeling stage ahead of time, right? That is the philosophical idea. And so basically what we want to do is we want to embed machine learning algorithms within legacy numerical solvers, right? This is against the scientific machine learning approach typically where or at least the one that I mentioned here, where people or researchers tend to not solve any system of equations at all, right? They want to do a data-driven optimization, but impose constraints of these physical systems in the weak sense, right? Whereas over here, we want to embed them within numerical solvers, and a keyword over here is the legacy. So existing numerical solvers, which already go quite a fair distance in solving these equations accurately. Okay, I have some terminology over here that will become clearer as we go along, but our goal is to learn corrections in an a posteriori manner. So what that means essentially is that we want to learn corrections to our numerical solvers using data in the sense of an inverse problem formulation. So rather than fitting a model to correct numerical solvers ahead of time, we correct numerical solvers during the learning process itself. But this will become clear if it's not very clear to you. This is a very it's a turbulence modeling type of terminology. But also this addresses the fact that we want to use varying sources of data and hopefully also lead to scientific discovery, which I have examples to convince you. Okay. All right. So I'll start with some background information that will make it easy to start with some experiments. The approach that we use, for many of our methodological development can conceptually be related to the neural ordinary differential equation idea. The idea is that if you have snapshots of training data that are temporal snapshots, so snapshots at different time instances. These can be even or uneven. Then our goal is to do a system identification of a system of ODs or PDs where the snapshots are generated by a time evolution of this system. So in the sense of a PD that is discretized by method of lines, U would be the discretized state variable, and our goal would be to learn the right-hand side. So in some sense would be to learn the acceleration, right? The right-hand side for a neural ordinary differential equation is typically modeled as a neural network. It can be other things. For example, if people are familiar with symbolic regression with SINDY, sparse identification of nonlinear dynamics out of the group at Washington with Steve Brunt and Nathan Kutz. This can be a library type term as well, but for today's talk, let's assume that this is a neural net. And the goal is to minimize a loss function. Again, we still assume that it's a mean squared error, and I'll show you examples where this is insufficient. But the idea is that your identified model is going to generate some trajectory by using a classical ODE solver such as RK4 or whatever, Euler even. And then your ground truth is also available because you've collected it from either from some numerical simulation or for some experimental data. And your goal is to match the predicted trajectory versus the ground truth trajectory, right? And so this is done by implementing this in a differentiable framework. So if you can back propagate or if you can compute gradients through this time integration, then you can compute the gradient of a loss with respect to these parameters theta. That deserves its own few slides. I will not go into it over here, but I'm happy to discuss it with you going forward. How to compute gradients of this loss with respect to this theta is essentially a little bit of calculus that you have to do. But the gradients can be computed using automatic differentiation, which is if you pick up a language such as PyTorch or TensorFlow, and you just implement an OD integration in there, you can just compute gradients just by calling torch.backward or tf.gradient, right? Automatic differentiation. But you can also write down the adjoint of this and then numerically solve the adjoint to compute the gradient of the loss with respect to the parameters theta. Anyway, those are details, but just to know that it is possible to optimize for theta for a wide class of problems. Okay. All right. So let's start with a simple experiment. We will start an experiment, discuss how classical methods fail, and then propose methodological improvements to address this. And that will be the general theme of the talk, right? Different experiments and how they challenge the foundational methods. So we'll start with the KS equations, so Kuromura-Shirosinsky equations. This is a PDE that I certainly like to work with because it gives rise to some interesting emergent phenomena. It's composed of an unsteady term or quadratic nonlinearity, such as one you might get in burgers. But then its linearity is a negative second order and fourth order term that actually causes very interesting behavior in the evolution of the problem when you solve it using a spectral code, like when you solve it exactly, right? So we'll add some more conditions. We assume that the system has periodic boundary conditions and is discretized, right, in one dimension. This is a one-dimensional system. And of course, if it is discretized appropriately, then you get what is deterministic chaos. So we'll see that in a bit. We add some other restrictions, and these restrictions are imposed to make our the life of the standard neural OD a little difficult, right? So we assume that there is only partial knowledge of the terms of the right-hand side. So the right-hand side is this quadratic nonlinearity, and then this complex second and fourth order linearity. We assume that we don't know these terms, but we know that this is a dynamical system that has a deterministic chaotic behavior and is dissipative in nature, or we make that assumption. So it is not a bad guess to assume that there's a nonlinear term and a linear term. That's all we guess, right? There's a linear term and a nonlinear term that are composed additively. The other thing is we impose a restriction on the amount of data that we're collecting. We only assume that we only have short-term history of the state evolution, right? So this is a chaotic system. So in essence, we can keep integrating the system in time forever and forever, and it will continue to give you like a chaotic system. There is no fixed point. It's not a dynamical system that's stable in that sense, right? But we assume we only have a short-term history of the state evolution, and we impose we impose on ourselves a task which is that we want to learn the evolution of these equations using these two restrictions, right? But what we want to learn is the long-term behavior of this system, right? So we want to, from the short-term behavior, we want to see how does the system behave in the long term where I did not have any data, right? And can we learn something about the system, which is the idea of scientific discovery, given that we only have short-term data, right? So that is our problem. Okay, in response to that, we, as you might guess, the standard neural OD does not do so well. So I will quickly introduce what we propose to address this issue first, and then kind of walk you through some interesting results. So the first thing we do is we impose our partial knowledge about the case equations into a new type of neural OD, which we call the stabilized neural OD, right? What we impose is the fact that our unsteady term du by dt should have a right hand side which is given by linearity and a nonlinearity, right? As against a regular neural OD which just learns the right hand side completely, because the idea is a neural network can approximate any function, so it can also approximate the composition of a linear and nonlinear one. In contrast, our approach is to impose a learnable linear as well as a learnable nonlinear function, right? And we impose some constraints on the linear term. We said that the linear term is symmetric and banded because the linear term behaves like a finite difference stencil. That's the only thing that we impose. So depending on the order of the linearity, we can have a like a plus minus one stencil or a plus minus two stencil. That depends on what prior information you want to impose on your linear term. But essentially, both these approaches have the same loss function, right? So the first one and the second one are still trained using mean squared error. The only difference is now we have this interesting inductive bias or interesting constraint that we apply on the linear term in one of them. Okay, so the statement of optimization has not changed. We still want to predict short-term behavior. And as you might guess, we want to assess the long-term behavior of these different models and see that they might be slightly different, right? So how does this look like in terms of results? So let's look at some qualitative assessments first before we go into some more quantitative results. So the top row is our ground truth given an initial condition sampled from the attractor. We want to first do a short-term evolution, then integrate it for a long amount of time. And the second column is the long-term. So if you look at where my pointer is, this is the short-term evolution. So the discretization we used was 10 to the negative 3. So this is about 50,000 time steps. Well, this is several more, maybe order millions of time steps. So in the short term, what you see across all the different methods is that they look virtually the same. So the first is the ground truth. The second is a standard neural OD. The third one is a neural OD, which we call it the fixed linear, because in this case, we actually specify the right A. So we actually discretize these two terms and we impose it here. So it's like learning only the nonlinear term. And the fourth approach is where you learn both the linear term as well as the nonlinear term. So that's the last one that we call CNN. Okay. And again, in the short term, they're all doing about the same. In the long term, as you can see, if you have a standard neural OD where the right-hand side is just a black box neural net, you see most of the times it would actually lead to overflow. But in the rare occasion that it's state bounded, you would get obviously non-physical behavior in the visual sense qualitatively, but I will show you quantitative results. In the case of using a linear term, you could see we could visually get more physical results, right? And this was backed up by quantitative assessments, where if you looked at the short-term evolution of our systems in the sense of mean squared error, averaged over different initial conditions, an ensemble of different initial conditions, you could see that the three different models were doing about the same, right? So this is like the error is low initially, chaos kicks in, so the error keeps growing, and then eventually it saturates, right? This is what you expect in the short term for the chaos equations. So nothing surprising. Any method would give you this behavior, but in the long run, we can. The chaos is a very unique and very interesting system of equations that admits an invariant metric. So if you plot a PDF of the second derivative of the state versus the first derivative of the state, the chaos equation should recover this very this very interesting sort of teardrop shaped attractor that the proposed methods, both where you explicitly fix the linear term or you learn it, are able to recover, but a standard neural ODE is not. So now I want to impress on the audience the value of this plot over here, right? We never knew about this PDF, right? We never knew that there was this emergent behavior from our data, and there is no way to optimize against this, right? This is something that you cannot define a squared error or any sort of differentiable metric for. And this is also computed after very, very long rollout. So there's no way to put this into an optimization formulation without suffering immensely high memory costs. But our method was able to recover this emergent phenomena just by virtue of embedding some information about our system into the right-hand side. So that's the idea of our approach to scientific machine learning, our approach in our group, where we want to sort of embed science about our knowledge about our system in such a way that we can capture, of course, the right behavior in the sense of the optimization metric, but also emergent phenomenon, right? Okay. The other nice thing about this approach is once you actually learn the linear term, so let's say you go back here and you're able to learn this term, so this case over here, the bottom case, this case over here, then you can actually perform an eigen decomposition of the linear term and obtain a set of coordinates. This is based on the theory of approximate inertial manifolds, which was pioneered by Yanis Kavrakidis in the early 90s in the chemical engineering community. You could find a projection matrix where you can convert your neural ODE into a system of resolved and unresolved coordinates. So dp by dt is the resolved coordinates where you basically project your original state based on the projection matrix you obtain, and then q is the orthogonal complement of p. So you get a set of resolved and unresolved differential equations, and you can close the resolved differential equations by just assuming stationarity of the unresolved ones. dq by dt equals 0 sets up this equation. And to identify this projection matrix, the eigen decomposition of A will actually admit basically a series of coordinates where you can actually identify that there are uh, there are coordinates where your data is actually varying in time, like your training data. So what that tells you is that our approach not only learned an A matrix, but it was also able to learn a low dimensional behavior of the KS equations that is actually well known in theory. So it was able to also identify that the fact that our data resides on a low dimensional manifold, right? And so this shows up also when you compute this projection matrix, but gradually add the number of eigenvectors to this, right, based on this non-stationarity criteria. As you add more eigenvectors, then I want you to follow the orange boxes here. As you add more eigenvectors, initially with just a few, with just 11, you get a high error. This is the KL divergence for the difference between this guy and this guy. So the difference in density space. There's a higher error, but this basically drops down to 0 as you hit like the theoretical dimensionality of the KS equations, the underlying manifold. The other approaches over here are methods where you basically build in a closure. So for example, instead of just setting Q equal to 0, if you set Q equal to A inverse capital Q of P, then you basically you basically recover faster decay, but the trend is similar, that you basically have high error as you keep lesser coordinates, right? So this is kind of what I call flipping the script, right? So we basically, instead of learning a surrogate model and then just using it, not only do we get a surrogate neural OD, but we're also able to identify a low dimensional structure, recover an emergent property, and also identify a like a reduced order representation. So we're able to reduce the dimensionality and accelerate the evolution of the model. So this is quite nice. Okay, so any questions over there, or can I continue? Okay, I will continue. So the idea is to build on top of the success of the previous set of slides. In many applications where you're actually solving complex, in my case, fluid flows, but complex physics, you typically have an existing solver. This could be a finite element solver, a finite volume solver, a DG solver. And the idea is that these solvers have some underlying governing equations built into them, such as over here the Navier-Stokes solutions, Navier-Stokes equations, and we in some sense we don't want to kind of approximate both the known and unknown operators, but if there is an operator that is known, such as this fixed linear case, we want to impose it and then just correct what is known. So this is kind of similar to like closure modeling, right? The difference is that now our neural network has to be trained within the forward solve of a discretized system of equations, right? So du by dt will be given by r, which is an operator coming from a numerical solver, and then the f would be something like a neural network. But this entire combination would be discretized both during training and testing. So that is a engineering challenge. I'll give you an example, a slightly more complicated example to motivate this. So for example, let's say we have for now a two-dimensional Navier-Stokes problem in incompressible with incompressible flow, and our goal is to calibrate a closure. So this is discretized on a coarse grid, and we want to correct the evolution of this model using a stress tensor that is learned. But we don't have access to anything like direct numerical simulations or high fidelity data to calibrate this tau ahead of time. So what we do is we just have ground truth in the form of experimental sensors. I have a schematic that will make this clear. The idea is that, okay, this tau term can be learned by a machine learning model, where we impose some constraints on how this machine learning model exactly behaves. For example, we'll say that it is a composition of a native viscosity model and a nonlinear model. These are details. Based on your application, you could have different prior knowledge about how this term behaves. The idea is that we impose this and we learn some coefficients rather than learning the tensor directly, which makes the learning problem a little easier. The problem that we're looking at is a backward facing step. So it's a nice problem because it's a benchmark for CFD, but it also is characterized by many features which make it actually quite difficult for machine learning or computer vision based methods, right? So for example, this is a model that has extreme anisotropy in the grid. So there are discontinuities, there's weird stretching. And so you can't just, git clone a machine learning model and just apply, the training data from this case in that modeling framework. So this requires a little bit of thought before we can actually deploy it in the differentiable physics setting that I was talking about, right? So let me introduce the learning the data in a more sort of coherent way. The idea is that I have flow over this backward facing step. I want to calibrate a closure to this because it's on a relatively coarse grid. But the only data I have to learn this closure is at these dark locations here downstream of the step, where I have data coming from, in this particular case, a fine grid simulation, but it could also be from some experimental data, right? So these are locations where I sense my flow field from ground truth, but our goal is to improve the closure all around the domain, right? And so this is a realistic example where perhaps you don't have the experimental budget or even the computational budget to sense everywhere, and so you kind of set up a constrained problem, like an inverse problem, right? Okay, to go and set up a differentiable physics formulation, the idea is similar to what happens in a neural OD, where you discretize a system of equations and then backpropagate through them. The difference here is that now your system of equations is coming from a finite element solver. In our case, could be a finite volume solver. In such a case, what we need to make this framework work is an adjoint model, which means that while we are learning the stress term on the right-hand side of the governing equations, that comes from a machine learning method here, I will introduce it in a bit. It's a graph neural network. This predicts the stress tensor at every given point. That goes into our finite element solver. Then we need the adjoint of the finite element solver to basically use calculus, the chain rule of calculus, to construct the gradients of the loss function. The loss function, I remind you, is still a mean squared error in the trajectory of these locations. So at these locations, we compute the trajectory of the ground truth and the prediction, and we then compute the gradient, right? So, so we need to be able to differentiate through our finite element solver to make this possible, right? Now, to deal with the fact that our data set is actually unstructured, we have to use geometric deep learning, because we cannot use CNN or one of these structured grid representations. This probably deserves its own talk, so I'm going to go through this a little quickly. The idea is that we have data that rests on unstructured grids at nodes, and there are edges that connect nodes. And the goal is to approximate a function on these at these nodes as a function of both neighboring nodes as well as the edges that are connecting them. So basically, we have a neural network that takes in the inputs of nodes and edges to update nodal values, and then nodes to update edges, right? So this is if this is unfamiliar to you, then think of this as a nonlinear variant of how one might compute like a finite volume type of cell update, right? So you have cell-centered variables, and we have fluxes that connect cells. Fluxes are computed using neighboring cells. So those are edges in the graph neural network. And so the fluxes themselves are used to update the cell values. Those are like nodal updates. Think of it that way, except that these are nonlinear, right? So there's a nice analog between finite element and finite volume methods and graph neural network methods, right? The other problem with using, like, say, something like a standard graph neural network for our approach is that we in CFD you deal with meshes which are very, very large. And again, this probably also deserves its own talk, but we developed a new method in our group where we are able to approximate functions on very large meshes by being inspired by like the ideas of multigrid methods. The idea is to build successively coarser meshes on which this message passing operation can traverse larger distances. So the concept of the neighbor is farther and farther away. And this lets you effectively approximate functions on very large meshes, which you cannot if you just use a single a fine mesh on which you have to do many, many operations before non-local information is propagated. So again, in an incompressible flow, non-local information is propagated rapidly because of the pressure-Poisson equation. So this is a crucial step. But I'm happy to discuss this with people in the audience later. But this is an interesting idea on how we can approximate functions on meshes more efficiently. Okay, so in terms of our problem, let's go back to our problem. Our goal, I remind you, was sensing the ground truth over here of fine scale simulation, still LES because it's 2D, is sensing the ground truth downstream of the step over here, and then trying to improve the simulation all over the domain. If you compare it with a model where there is no closure, so no stress, you see that there are higher errors near the walls. This is something that we want to avoid. Assuming that you do have some sort of closure, these two models are closures that are like classical closures, where we take a Smagorinsky type of approach and we specify a static coefficient, which is manually hand-tuned. Then you see that you still have some errors. There are still some gray regions, but it's improved compared to no closure. But then if we have our dynamic adaptive closure, where graph neural network is predicting the stress everywhere, then you see you have the lowest error. What we want to look at is, for example, the performance of our model at a particular locations. For example, this probe location, where we did not sense anything during the training process. And you can see that by specifying a closure where we are sensing downstream of the step, we are able to compare to, let's say, just the manually chosen LES closures like a Smagorinsky closure. We are able to, in addition to this quantitative sort of approach, we're able to get a closer agreement, at least early on, to the right amplitude and phase of our oscillations at that probe location. Of course, over time we do kind of get a little poorer, but it's much slower than these models over here. So just to add a little context over here, we actually trained for the first 0.02 seconds, and then kind of unroll this out as a just like a regular LES, right? And of course, we get a speed up by using the machine learning model. That's obvious, otherwise we wouldn't do this. But we also want to be honest and say that our training time, takes 6 hours on 100 to train this. So we want to optimize this, but it's also important to think about cost amortization if we are trying to deploy these methods for downstream applications, right? But really, I promised you that one of the things you're most interested in is basically scientific discovery, right? So if you go back to my formulation over here, where we had where our machine learning framework is trying to predict tau, but indirectly learning this coefficient C sub s as well as these coefficients k, alpha, beta, and gamma. The C sub s is a coefficient that basically activates the turbulent eddy viscosity, so it activates where to dissipate the flow field, dissipate turbulent kinetic energy. And so even though I have sensed downstream of the step over here, you can see that my model has actually learned to activate the Smagnitsky coefficient near the step. This makes sense because it has to match the right shedding period, right? So frequency. So this is what I mean by scientific discovery, that we didn't impose prior knowledge about the fact that this should be desirable, but it was backed out by the fact that we had some sparse observations about our state, right? And so you can think of this being generalizing to many different applications. Instead of learning a subgrid stress, we could think about learning boundary conditions on the walls, right, for the wall model. Or we could think of, I don't know, learning a discretization as well. So there are many possibilities over here. The fact that we use a graph neural network makes it easy for us to actually deploy this method for cases. The video is a little jittery, but because it's kind of heavy, but we are able to actually also deploy the train closure on different geometries. Of course, we should be cautious over here because these geometries need to have, in some sense, a similar type of physics. So over here, shedding over an object mounted on the floor. But you can see there's a similar type of activation of the Smagnitsky coefficient in all these cases. These are unseen cases with different geometries, but the idea was that our machine learning model should be able to, reactivate itself in a similar manner, right? So this was also nice. So it's viable for, generalization to applications that are similar physics, right? Okay, so right now we this is still early days, but we are extending this to 3D, and so we use Phoenix for our finite element solver. But our hope is to basically recover, similar types of results with a training that is done in 3D and also deployment that is done in 3D, because that would then start, actually helping us incorporate experimental data into our learning process. So, so this is something that we are very excited about. Just wanted to give you a quick update on that. Okay, I have 15 minutes left, so let me speed up a little. I promise to leave some time for questions. Another nice reason about using these embedded neural networks in the differentiable physics formulation is that they are amenable to a little bit of error analysis. So if you do like an error analysis of discretized ODEs in the sense of the time integrator, you can actually bound the posteriori error for this for the performance of this solver plus neural network combination as a factor of grows exponentially with respect to the Jacobian of the right hand side. So this is something that was really amazing when it fell out of our analysis, because there were papers in about almost 6 or 7 years ago which saw that if you did a neural ODE, a standard neural ODE, not the differentiable physics idea, and impose the Jacobian of the neural ODE as a penalty, so make the Jacobian small, then they got better errors during rollout, which was implicitly kind of shows up in this upper bound that we computed, So the R term over here is the Jacobian, the 2 norm of the Jacobian. So as you can see, if the 2 norm of the Jacobian is larger, then the error grows exponentially faster. So this was independently sort of sort of derived in a paper that we have under review, as well as another paper from Los Alamos. So this is also another nice reason to use these methods, because typically if you have a priori models for the stress tensor, then there is no way to compute this bound ahead of time. Okay, so again, 40 minutes left. Let me, there might be people in the audience who have this question, and so I want to preemptively give you some philosophy on that. In many cases, the mean squared error is not a good metric to optimize. So for example, if you think about chaotic systems, such as the Lorentz equations, how do you learn through a chaotic system? Because the mean square error does not make sense. Two trajectories which are infinitesimally perturbed at the initial condition will stay together for a short amount of time before diverging and never seeing each other or never staying close to each other in the future. They may intersect, of course, in phase space, right? And so the Lorentz 63 system is an example of this, right? So there is some structure in the system, which is of course nice, but there is no way to optimize through the structure, right? And so there was this work actually done at MIT by Professor Chi-Chi Wang, which was aimed at computing useful gradients of such systems, which is called least square shadowing. I don't have the time to go over least square shadowing in this talk, which is a very mathematically rigorous and kind of extensive approach to computing sensitivities of chaotic systems. But the problem with that approach was that you would have scaling issues, because you would need cubic complexity in the sum of the dimensionality of the state and independent variables. So like for Lorentz 63, it would be 3 plus 1 if you are taking the derivative with respect to one of the independent variables, right? So 4 cube, which is quite large. For a realistic system, this could be millions, so you're out of luck. So to motivate this with a very simple example that everybody can identify with, let's say I do have Lorentz, right, as you see over here, and my objective is to find the gradient of z bar with respect to rho, where z bar is the time average z, right, the long time average z. You can see that if you actually plot j, right, if you actually plot the time average z for different values of rho, to the naked eye, it looks very simple, right? It's just a straight line. You can easily like eyeball what the slope is over here and compute dj by d rho. But if you are to do this using automatic differentiation or finite differentiation, so basically where you compute z bar and then you try to compute d z bar by d rho, you will see numerically, you will see that the gradients are absolutely horrific, right? You cannot, these are not useful for anything, whereas the actual gradient is much more nicely behaved, almost identity. And the reason of this is because if you zoom into this line over here, you will see that it's very non-smooth, right? So you can't really compute the exact gradient numerically, because this line is in some sense kind of like a Weierstrass type of function, right? Okay, so to deal with this, we were inspired by some recent work at UIUC by Jonathan Freund's group, which the reference is over here. The idea was that instead of computing gradients of an entire trajectory of a chaotic dynamical system, which, as you can see over time, the two trajectories do not match each other and then cause basically impossible gradients, we can chop up our trajectory into multiple non-overlapping windows within which gradients are well defined, right? So you can think of computing a gradient for this loss, this loss, this loss, this loss, and averaging them. So that's fine. That's easy to do. But then also imposing a weak constraint such that the final position of the trajectory of the first window should match the initial condition of the trajectory of the next window, right? So this is a weak constraint. Effectively, it turns out into a loss function where we find the losses within windows, right, as I mentioned, but also learn the initial condition for successive windows. So the idea is that we want to learn the initial conditions at these locations, Q1 plus Q2 plus Q3 plus, in such a way that the starting position of the next window is close to the ending position of the previous window. But the interesting thing is we add a penalty to this term, which is initially weighted very less. So initially, our optimizer, tries to learn the short-term behavior of the dynamics very accurately, and then eventually it starts penalizing the fact that the dynamics are diverging, but also in the loose sense, not in the hard sense, right? And so, of course, again, going back to the concept of no free lunch, um, while you do not have the cubic complexity problem, because automatic differentiation for using this is linear in nature, linear complexity, what you do have is more memory limitations, because now you not only learn the parameters of your neural OD theta, but you also learn the initial conditions, and the initial conditions are quite large, right? So they are, like if this is a turbulent state, this is the initial condition of a turbulent state. So it's not easy, right? But assuming that you have enough memory, you can actually learn this system quite well. So if you go back to the Lorentz problem and you plot with respect to two parameters over here, the loss, you can see that the loss function is very, very sort of kinky because of using the exact adjoint. Whereas if you add this penalty term and allow for small discrepancies at the intersection between windows, you see a much smoother loss surface, which can be used for optimization, right? So again, I'm running out of time, so I haven't timed this pretty well, but I will quickly accelerate. So we take this idea back to our neural OD, and we go back to the KS equations. In this case, again, we have to learn both the parameters as well as the initial conditions of successive windows. And when we do this, what we see when we look at the invariant measure is that this is the true invariant measure, which is the teardrop shape attractor I talked about. There's an island that falls out of it. If we use the stabilized neural OD, where we actually explicitly had knowledge of the right-hand side, you can recover the island. But what we have in this plot over here is something that qualitatively looks similar, but I have basically just used an improved optimization formulation for learning chaotic dynamic systems and not used any knowledge of the right-hand side, right? So no linear, nonlinear decomposition. So this is in comparison with the neural OD, which is not able to get the qualitatively right behavior. But as you see, so what you take away from this slide is that if you know something about the physics, of course you should use it. That gives you the most superior performance. But if you don't know enough, then an improved optimization algorithm is certainly also going to help you, right? Okay. Another way to check for the emergent phenomena of our trained models is something like the return period. So the return period essentially measures how frequently the y-axis is, you can think of the y-axis as steps, how many steps it takes for a maximum value such as the x-axis to return. So think of this as, for example, the maximum temperature of the planet of the Earth. If you have a 60 Celsius day, that happens vanishingly rarely, so that return period is higher. But if you have something like 30 Celsius, that happens much more frequently, so that shows up somewhere over here. And so as you can see, there's an exponential growth as the magnitude of the maximum KS solution grows. If you compare these three different models, the improved optimization algorithm, the vanilla, as well as the stabilized approach, and the ground truth, which comes from the spectral method. You see, if you add physics, you get closest, right? That's natural. But if you use an improved optimization algorithm, you generate extremes a little better than if you just fit the mean squared error for the short-term evolution, right? And it also shows up in the variance. So some analysis that tells you that emergent phenomena is really what you need to be looking at when you're doing machine learning, rather than just a mean squared error. Okay, so 5 minutes. I'm going to quickly wrap up. We took this idea to something that we really didn't have any physical knowledge about, such as the ERA5 data set. This is a benchmark data set for weather forecasting, where we had a right-hand side where we now just had a black box spherical CNN, and we wanted to learn the evolution of the weather. Again, in the short term, we are able to predict these 4 variables quite well. This is not important. What is really important is the behavior in the long term, right? So in the short term, you get similar errors, as you can see over here, right? across these two different methods. But in the long term, as you can see, for some variables, the neural OD error grows, whereas the standard method, the multi-point neural OD, so the one with the improved optimization algorithm, stays bounded. If you look at the seasonality, again, we are able to recover the right trends because of an improved optimization formulation. Better remember, over here, I've not imposed any physics at all. This is just learning from observations of the atmosphere. And what is really interesting over here is, and I'll stop here, this is a philosophical slide. The idea that machine learning can do everything. When we took this model for our atmosphere and we actually unrolled it for 40 years, our model actually showed us that the Earth was cooling, right? Which is obviously not right. So, and this told us that despite our fit for the short-term accuracy and using improved optimization algorithms, we were still getting the wrong, sort of emergent behavior. So when we went back and actually imposed carbon dioxide as an exogenous variable, so the amount of carbon dioxide released by anthropogenic sources, then we were able to fix this model and actually obtain the right heating as well. So our model was also predicting global warming once carbon dioxide was forced, right? So the philosophy here with the slide where I stop is that, it's good to build better algorithms, but the scientist always has to stay in the loop to make sure the results are sensible, right? So if people are automating the process of doing science with AI, then it's still some distance in the future. Okay, so anyway, I will stop there and say that in my group we are very interested in various ideas like this that go beyond just the use of machine learning, but also its use for scientific discovery. So I will stop here. I know I went way over time. I'm really, really sorry about that, but I'm happy to stick around and take questions and follow up with you via email or otherwise. Yeah. So thanks a lot for inviting me to speak.
Yeah, great. Thank you so much. Thank you so much, Romit, for that nice talk. Yeah, I'd like to open it up for any questions or comments from our audience. So please feel free to unmute yourself if you have anything you'd like to say, or raise your hand.
Romit, this is Matteo speaking.
Hi, Matteo. How are you?
How are you? I'm good. Well, first of all, thank you very much for giving us this talk, and it's very inspiring to say the least. And I have a question which is more philosophical than technical. How about multi-phase flows, right? So presence of interfaces and forget about either mass transfer, but just multi-phase flow, water, say gas, liquid. What are the, what is your opinion? What is your view on what we'll be able to achieve on multi-phase flows in the, say, next 5-10 years?
That's a difficult question for me to answer because I haven't really worked with them much to put my to give you an answer one way or the other whether it will or will not work. But my understanding is that if you frame machine learning, the way I do it is I frame it as an inverse problem where I kind of impose the physics that I know and I'm confident about, I don't throw it away, right? So there's one school of thought which says that the data is enough, right? So we can kind of learn everything from the data. So if you have lots of simulations of multiphase fluids, then you can just put it into like a vision based model, and then it'll generate emergent, like sort of physically realistic multiphase quantities of interest, right? Because I guess as engineers we care about eventually quantities of interest. But the way I do my work is, if you know about equations, then we should probably impose them into our methods, such as when I was doing closure, I was imposing the structure of the closure, the fact that it has a like a tensor basis expansion, right, with Cayley-Hamilton, right? So in that sense, I am optimistic, right? So if you can like sort of build in transport laws into our machine learning framework such that it preserves like these constraints, then and we design the corrections to those laws in such a way that they don't affect those constraints, then I think I think it's optimistic, right? So some other work that we're doing is I think even more compatible with what you mentioned. We're actually learning adaptive mesh refinement schemes with data, right? Rather than correcting the governing laws or learning new governing laws, we say the governing laws are great, but it's resolution that's a real problem, right? The mesh, because CFD people will say the mesh is 90% of the battle, right? So so there are, in our group, we're developing a code which lets you dynamically adapt the mesh, but not based on any a posteriori error indicator, but actually like a machine learning model that can dynamically adapt the mesh given like training information, right? So now what we are doing right now is we're actually doing a digital twin of the AMR process. So if we are able to do experiments of our actual problem, and we collect that data, give it to an agent that then tells me what mesh to use in real time, right? So that way, as the engineer or the scientist, you don't have any stress at all about the governing laws not being satisfied, because I'm just giving you the mesh, right? You're using the mesh with your well-known solver, and 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 we can build in some guide rails in our meshing strategy to make sure that it's not going to violate some base quality requirements. But once you solve the solution on that mesh, it's going to satisfy all the constraints that you want. So so that's something. So basically, the answer is we got to be creative, right? We have to be creative, and we have to think about these problems not as a sort of a monolithic method that we just apply to everything, right? So yeah.
All right.
Mhm.
I have to go. Thank you very much. I'll follow up with you.
Sounds good, Matteo. Yeah,
Okay,
thank
bye.
you so much.
Thanks.
Yeah,
Bye.
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 Great.
I had a question if we have a couple minutes. Is that
Hi,
is that
Suhas. Yes, of course, for you. Yes.
Hi,
Yeah,
Romit.
yeah.
How's it going?
Good. How are you?
Good. So I guess like the turbulence modeling case that you showed. So I guess my question there was like, is the advantage that you're incorporating the errors, the truncation errors and those things in your model, as opposed to, for example, let's say just
Yes.
training in a priori sense the tau operator and then using it for during the inference stage.
There is one advantage. The second advantage is I don't need DNS, right? Because I need an observation operator. So the state is produced by the LES plus model, right? And initially the model is garbage, the state is garbage, but I can apply an observation operator on that garbage output, compare it to something that can come from some other source. It doesn't have to be DNS anymore, it can be sparse. Then I minimize that distance, and hopefully the closure is the one that's forcing the eventual LES close to that, right? And so I don't have to make any assumption of filtering. I don't have to, yeah. So those are the benefits, right? So the truncation error gets rolled into that as well. So this is a bit that these are the two schools of thought in data-driven closure, right? The a priori approach says that if I have DNS, I can compute the stress, and I can learn it, right? But that usually it places very strong assumptions on the nature of the filter, because in many cases it's difficult to tell what the filter is, right? I mean, on a structured geometry, finite volume, okay, maybe you can use this and that, right? But and so like, for example, I can send you a paper of mine. This approach that we are putting together is able to capture backscatter without injecting too much energy into the supergrid, right? And so we are able to like stay stable indefinitely and generalize to different geometries also. So yeah.
That's interesting.
So it's closure as an inverse problem, right?
Yeah.
So
yeah, it was good, really nice presentation.
thanks to us. Yeah,
Yeah.
happy to chat more.
Okay, amazing. Yeah, so if there are no more outstanding questions, I think we can go ahead and conclude. So yeah, let's thank Dr. Romit Maulik for again giving this nice talk. So thank you everybody for attending and being part of this. We have our next talk April 9th. I'll send a calendar invite for our next speaker on that one. So yeah, thank you everybody again. And, Yeah.
Thanks,
hope to see you
everyone.
soon.
Happy to chat offline as well. All right. Thanks a lot.